All right, let's talk about something that's at the absolute heart of JavaScript, but still manages to trip up almost everyone at some point, the event loop. Seriously, if you've ever built a beautiful UI only to watch it grind to a halt, you're in the right place. I'm sure you've been there. You've written some code, it looks perfectly fine, maybe it's even async. You click a button, a little spinner pops up, and then dead. The whole page is just locked solid. It's gotta be one of the most frustrating things in web dev, right? Well, here's the twist. Most of the time, the problem isn't that your code is slow. The real culprit is when your code runs. It's all about scheduling. And that's the mystery we're going to unravel today. Okay, so to get to the bottom of this, we have to start at the very beginning, the one place where all of your JavaScript code actually runs. This is our first clue, and it's called the call stack. Think of the call stack as a single lane highway. It can only handle one car, one task at a time. And while it's busy with that one task, even if it's a really, really long one, the entire highway is blocked. No other cars can get on, no clicks, no animations, no updates, nothing. This single-threaded nature is the root of every single UI freeze. And this right here, this is a huge misconception. We tend to think that using things like async and await or promises is some kind of magic that makes our code run in parallel, but it's not. All they do is take a chunk of work and politely ask the event loop, hey, can you run this for me later? That code will still block that single lane highway when its turn finally comes. So if async is just about scheduling work for later, what does later even mean? Well, it turns out there are two very different kinds of later, and knowing the difference is everything. Let's meet the two main characters in our story, macro tasks and micro tasks. Here's an easy way to think about it. Macro tasks are like scheduled appointments in your calendar. Think a set timeout or a user clicking on something. They're individual, standalone jobs. Micro tasks, on the other hand, are like urgent sticky notes. They're the, oh, and one more thing that needs to happen right now after your current task finishes, like the code inside a promise.then. And the keyword there is priority. Micro tasks always cut to the front of the line. Okay, we've got the call stack, we've got our big macro tasks, and our urgent micro tasks. So how do they all play together? It all comes down to one simple, strict, and totally non-negotiable rule that the event loop lives by. This is the secret sauce. And this is it. This is the key to everything. The event loop will pick just one macro task from the list and run it. After it's done, and this is crucial, before it does anything else, it will run every single micro task it has until that list is completely empty. Only then, once all that work is done, does the browser finally get a chance to breathe and update the screen. Then the whole cycle starts over. One macro task, all micro tasks, then maybe a render. That's the loop. Theory is cool and all, but let's see how this plays out in the real world. I'm going to show you a classic little code snippet. Based on that one loop rule we just learned, take a guess at what gets logged to the console. So what do we have here? We've got a set timeout, which we know schedules a macro task. Then we've got a resolved promise, which is going to schedule a high-priority microtask. And finally, just a plain old console.log, which runs synchronously right away. Did you get it? The answer every single time is sync, then promise, then timeout. It's not a race, it's the rule. First, the synchronous sync runs on the call stack. The loop finishes its current task. Then, step 2, it checks for microtasks. Hey, there's our promise. It runs that logging promise. The microtask queue is now empty. Finally, in the next turn of the loop, it gets to step 1 again and picks up our set timeout macro task, logging timeout. See? Predictable. Okay, so knowing the rule is like having a superpower. But, with great power comes the ability to shoot yourself in the foot. Let's look at a couple of ways this system can go terribly, terribly wrong. This first trap is a real nightmare. It's called microtask starvation. Remember step 2, drain all microtasks? Well, what happens if a microtask schedules another microtask? The loop has to run that one too. And what if that one schedules another? You see where this is going. You can get stuck in an infinite loop of microtasks, and the event loop never, ever gets to step 3. It never renders. Your UI is toast. This quote just says it all, doesn't it? It's so dramatic because the situation is that bad. Because microtasks have that VIP front-of-the-line priority, the browser is completely stuck. It can't handle the user's next click. That's a macro task. It can't paint the next frame of an animation. You are trapped. And all the user sees is a page that's completely frozen. Now here's a sneakier trap. Let's say your promise fetches some data. Great, but then in your .then block, you decide to do some really heavy, complex data processing. Well, guess what? All that heavy lifting is running as a microtask. And because it's a microtask, it's blocking the browser from rendering until it's done. So even though your code is async, the user just experiences a long, painful freeze. All right, enough with the doom and gloom. Let's talk about solutions. Because once you understand these rules and you know the dangers, you can start being a master scheduler. You can actually use the event loop to your advantage to build buttery smooth apps. Here's your toolkit. The most important skill you can learn is how to yield. Got a heavy task? Don't run it right away in a microtask. Wrap it in a set timeout with a 0 delay. That pushes it to the back of the line as a macro task, which gives the browser a chance to render first. If you're doing visual updates, Request Animation Frame is even better. It's literally designed to sync up with the browser's paint cycle. And for those really huge tasks, chop them up into smaller pieces and schedule each piece with a set timeout. So to make it super simple, here's a little decision guide. Need something to happen immediately after an async operation, no matter what? A microtask is your friend. Changing something visually? Request Animation Frame is the pro choice. Need to do some heavy work but keep the UI responsive? Push it to a macro task. And if the work is just truly massive, get it off the main thread entirely with a web worker. So we've covered a ton of ground here, from the nitty-gritty of the call stack to these high-level scheduling patterns. Let's pull it all together into one big, powerful mental model for how to think about this stuff. If you remember one thing from this whole explainer, let it be this. The async keyword is not a magic wand for performance. A truly responsive app isn't built by just using async APIs. It's built by understanding the event loop well enough to know when your code needs to get out of the way and let the browser do its job. It's all about consciously yielding control back to the browser. So let's recap the big ideas. Microtasks are super powerful, but you gotta handle them with care, because they can be dangerous. Your browser can only update the screen when your code is not running. Remember that. And it's those long, chunky tasks that really kill the user experience. So the path to true performance isn't about writing faster code, it's about writing smarter, schedule-aware code. And that's really the question to take with you. Now that you know the rules of the game, how will it change the way you write code? The next time you're writing a promise chain or a complex event handler, you can ask yourself, hey, is this going to block the UI? Do I need to yield here? Mastering this is more than just fixing bugs. It's about fundamentally changing how you build for the web.